everyone. So once again, we will be discussing all about power for um, today. So since we are done with work as well as kinetic energy and potential energy, so we will proceed with power. So if we will define power, it is the time rate at which work is done. So also power is a scalar quantity. So we have this following equations. The first one is the average power. So for the average power, we have here P average is equal to the change in work. So big letter W is the work done. So change in work divided by the change in time. So this is our equation for the average power. Now, how about for the instantaneous power? For the instantaneous power, we have P, or the power is equal to, we have the limit at which your delta T approaches 0 of the change in the work done divided by the change in time, or we can also have it as the change in work over the change in time. So also, by the way, power is a scalar quantity. So when we say scalar, again, it has um, magnitude only. So it has no direction. So again, these are the equations for the average power. So again, average power is equal to the change in work divided by the change in time. Whereas for the instantaneous power, we have still the change in work done divided by the change in time. Uh, yes, for the instantaneous power. So now we have here in figure 6.25 as an example for the same amount of work is done in both of these situations, but the power or the rate at which the work is done is different. So for the first one, we have they have different they have the same work, which is equal to 100 joules. So as you can see here in the two situations, but they have different output. So in the first one, from t equals 0 to t equals 5 seconds, so your power output, which is P is equal to work divided by the time. So we have 100 joules divided by 5 seconds is equal to 20 watts. Whereas we have here the same amount of work, which is 100 joules, but you're given the time, which is 1 second. So the power output of this one, we have P is equal to work over time is equal to 100 joules divided by 1 second is equal to 100 watts. So again, they have different they have different power output given the same amount of work done. So depende on the time for you for the box to be lifted. So by the way, the unit for power is we have watt or watts. So if plural, we have watt. So the symbol for watt is capital letter W. So 1 watt is equivalent to 1 joule per second. So this is joule and this is second. Okay, diba? We have power is equal to work over time. So the unit for work is we have joule or joules, and we have the unit for time is in terms of second. So that's why 1 watt is equivalent to 1 joule over second, or 1 joule per second. So we also have other units of power. We have this one, HP. HP stands for horsepower. So 1 horsepower or 1 HP is also equivalent to 550 foot-pound per second, or we can also have it in terms of foot-pound per minute, which is equivalent to 33,000. So other also unit of power from horsepower to watt. So we have 1 horsepower is equal to 746 watts, or if we will convert it to kilowatts, 1 horsepower is equivalent to 0.746 kilowatts. Okay. Let's say, for example, the problem is giving you units in terms of like horsepower or kilowatts. So at least you know how to convert the following units into our basic unit or SI unit for power, which is in terms of watt or watts. So again, other units of power, we have HP or horsepower. We also have kilowatts. So this one right here is kilowatts. And then we have in terms of foot-pound per second or foot-pound per minute. So again, those are the other units for power. Okay, so in mechanics, we can also express power in terms of force and velocity. So not only in terms of work and time, but also in terms of force and velocity. So suppose that a force F acts on a body while it undergoes a vector displacement delta S, or the change in displacement. So if parallel force is the component of the force, vector force F, tangent to the path, or which is parallel to delta S, then the work done by the force is, we have right here, change in the work is equal to the parallel force times the change in the displacement. So now the average power is, so substituting kay, di ba, average power is the change in the work divided by change in time. So substituting the value for the change in work, which is parallel force times delta S. So our average power now is, we have parallel force times the change in the displacement divided by the change in time. Or we can also have it as the parallel force times, we have change and displacement divided by the change in time. So take note na delta S over delta T is just, or we can also have it as the change in distance over the change in time is equal to the average, V average, or the average velocity. Okay, so that's why we have this one right here. So average power now is equal to the parallel force times the average speed or average velocity. So now power is equal to parallel force times the velocity. So this is now the equation for power in terms of force and velocity. So also, if we will be having our equation in power in terms of dot product, we have P, or the power is equal to the dot product between the vector force F and the velocity V. So this is for the instantaneous rate at which force does work on a particle. So again, we have for the average power, we have the change in work over the change in time. We also have the formula for power in terms of force and velocity, which is the product of the parallel force and the velocity. Okay, so we have here an example of force and power. So each of the 4 jet engines on an Airbus A380 airliner develops a thrust, which is a forward force on the airliner, of 322,000 newtons, or it is equivalent to 72,000 pounds. So when the airplane is flying at 250 meters per second, or 900 kilometers per hour, or roughly 560 miles per hour. So what horsepower does each engine develop? So we are asked to solve for the power of this airliner given the force, which is equal to 322,000 newtons, and also we are given the value for the velocity or the speed, which is equal to 250 meters per second. So on the previous slide, we are given the formula for power, but first we will write the given values. So given values, again, we have the force, parallel force, which is equal to 322,000 newtons, and then also the speed, which is 250 meters per second. So again, we are asked to solve for the power in terms of horsepower or HP. Okay, so now from the equation, power is equal to the parallel force times the speed or velocity. So substituting their corresponding values, we have 322,000 newtons times 250 meters per second. So if we will calculate that, we will arrive at 8.05 times 10 to the power of positive 7 watts. Okay, so now we have an answer in terms of watts, but here the question is what horsepower? So we will convert horsepower, watts, 8.05 times 10 to the power of 7 watts into horsepower. So we have on the previous slide, we are given the conversion for horsepower in terms of watts or watt. So we have 1 horsepower is equal to 746 watts. So cancel out C watts here. So we are left with horsepower. So we have 8.05 times 10 to the power of 7 divided by 746. So the power of this airliner or A380 airliner is equal to 108,000 horsepower or HP. So this is now the value of our power of each engine. So we have, since each of the 4 jet engines, so each engine has a power of 108,000 horsepower. So this is for example number 1. Okay, so we also have another example or our second example. So a 50-kilogram marathon runner runs up the stairs to the top of Chicago's 443-meter tall Willis Tower. So this is the tallest building in the United States. So we have here the figure in figure 6.28. So to lift herself to the top in 15 minutes, the question here is what must be her average power output? So express your answer in watts, in kilowatts, and also in horsepower. So we will be expressing our average power output in terms of watts, kilowatts, and in horsepower. So okay, so given the given values, we have the mass of the runner, which is 50 kilograms. We also have the height of the building, H, which is 443 meters. And then also, we are given the time. So we are given the time of the runner, which is 15 minutes. So we also have here the time, which is 15 minutes. Okay, so 15 minutes, we will convert that into seconds. So 15 minutes, we have here 1 minute is equivalent to 60 seconds. So 15 times 60 is we have 900 seconds. Okay, so our time is 15 minutes, or it is equivalent to 900 seconds. Okay, so now here, before we can proceed with calculating for the average power output, we need to solve first for the work done by the runner. It's because to solve for the average power output, we need the work as well as the time, but we don't have any value for the work yet. So we need to solve for the work, or the amount of work done by the runner. So given only the mass, we have the height and the time. So we will be using the equation for the work done, yes, by the gravitational potential energy. So we have work is equal to the mass times gravity times the height, or mgh. So we have 50 kilograms times the acceleration due to gravity, which is 9.8 meters per second squared, times we have the height, which is 443 meters. So calculating this one, we have 50 times 9.8 times 443. We will end up with 2.17 times 10 to the power of 5. Again, for work and any energy, we have joules as our unit. So the work done is, we have 2.17 times 10 to the power of 5 joules. Okay. So now, since we have now the value for work, so we can solve for the average power output of this runner, which is, we have average power is equal to the work done divided by the time. So we have 2.17 times 10 to the power of 5 joules divided by 15 minutes, which is equivalent to 900 seconds. So our average work done, average power output, is equal to 241 watts. So since we will express our answer in watts, kilowatts, and in horsepower, so 241 watts is equivalent, if we will convert that into kilowatts, so we need to divide it by 1000. Okay, 1 kilowatt is equivalent to 1000 watts. So it is equal to 0.241 kilowatt. Okay. And then for the last one, yes, we will convert that into horsepower. So, di ba 1 horsepower is equivalent to 746 watts. Okay. So we have 241 watts, 2 horsepower. So we have 1 horsepower is equivalent to 746 watts. So 241 divided by 746 is equal to 0.323 horsepower. Okay, so we have now our values in terms of watts, which is 241 watts. In terms of kilowatts, which is equal to 0.241 kilowatt. And then in terms of horsepower, we have 0.323 horsepower. So this must be her average power output of this marathon runner for her to be able to lift herself to the top in 15 minutes. So also another there is another way to solve for the average power in terms of the force and the speed. Okay, so to solve for the force is equal to the weight of the marathon runner. So here, average power output is equal to the parallel force times the velocity. So we don't have any of these values right here, but we have the mass of the runner, which is 50 kilograms. We also have the time, which is 900 seconds. So to solve for the force is equal to the mass times the gravity, which is just the weight of the runner. So we have 50 kilograms times 9.8 meters per second squared. So our force is equal to, okay, let's calculate. 50 times 9.8 is equal to 490 newtons. Okay, and then to solve for the velocity is just, well, we have the force now. Now for the velocity, it is equal to the distance over time. So for the distance, we will be using the height of the building, which is equivalent to 443 meters. So to solve for the speed or the velocity, we have 443 meters divided by 900 seconds. So 443 divided by 900 is just equal to 0.49 or 0.492 meters per second. So we have now our values for the force and the velocity, so we can solve for the average power output. So we have 490. Okay. 490 newtons times the speed, which is 0.492 meters per second. So the average power output is still equal to 241. It is 241.08 watts, or we can just have it as 241 watts. So this is how we would solve for the average output in terms of force and speed. So we can solve it in two different ways. The first one is to solve first for the work done and then calculate for the average power output. The second one is to solve first for the force and the velocity and then the average power output. So that is our discussion for power. Thank you.